We're now going to start looking at field extensions in more precise and careful ways. Now, in particular, we're going to talk about what are called algebraic extensions. In order to simplify the statements of the theorems and the exposition, we're going to treat all of our field extensions as if they are containments. F contained in E, F and E, both fields. We don't actually lose anything this way, since if we have a general field extension, phi from F to E, remember that phi is a ring homomorphism and it's also injective, then we have that phi of F is a subfield of E, and F is isomorphic to phi of F. So we aren't actually losing any sort of generality, we're just making the statements of the theorems simpler in this case. And all of the theorems that we're going to say could be written in the more general style, but we really wouldn't gain very much there. So we're going to be looking at field extensions like this and talking about algebraic elements. Let's give a definition for that now. Definition 168. So let's let F contained in E be a field extension. We say that an element A in E is called algebraic over F if it is the root of some non-zero polynomial. Non-zero polynomial F inside the polynomial ring with coefficients in the field F, and is otherwise called transcendental. So given any field extension, you'll have some algebraic elements. In particular, every element of F is itself algebraic over F because it's the root of a linear polynomial. And then anything in the field E which isn't algebraic over F is called transcendental over F. One way of thinking about this is that algebraic elements are over F are things that can be described in terms of F, in terms of some sort of algebraic equation, some polynomial type of equation involving the coefficients of F. Whereas the transcendental elements over F are not related to the elements of F in any sort of algebraic way. We're going to be able to make this precise later on when we start describing what happens when we take the extensions corresponding to an algebraic element versus a transcendental element. Continuing the definition, if an element of E is algebraic over F, then a monic irreducible polynomial F in the polynomial ring over the field F, which has A as a root, is called a minimal polynomial for A over F. Recall that monic means that the leading coefficient is 1. So a minimal polynomial for an algebraic element will be a polynomial with leading coefficient 1 that's irreducible and has A as a root. Currently, we don't know that minimal polynomials exist, or how many they are, but that's going to be the subject of our first theorem. Finally, finishing up the definition, the extension field E is called an algebraic extension of F if every element A in E is algebraic over F and is called transcendental otherwise. A transcendental extension otherwise. So notice a slight asymmetry in the definitions here. If the field E is an algebraic extension of F, that means that every element of E is algebraic over F. But if the field is transcendental over F, that means that there exists some transcendental element in E over F, not that every element of E is transcendental over F. We're not going to have a term precisely to describe an extension which contains only transcendental elements here, although we could study that, and we're going to look at some things that are sort of related to that idea. So let's look at some examples. Let's look at the field extension Q contained in R, the rational numbers contained in the real numbers. In this extension, we have that the square root of 2 is algebraic over Q. And indeed, if we take any nth root of x for any natural n and any rational number x, these are all algebraic, since we have that this is a solution, since this element is a solution to the polynomial x to the n minus little x inside the polynomial ring over Q. However, we have that pi and E are transcendental over Q. Now, this is difficult to prove, and in fact, the fact that pi and E are transcendental over Q, that knowledge is less than 200 years old. It took a long time for people to prove that there is no polynomial that has pi as a root, or there is no polynomial that has E as a root. Proving that a number is transcendental tends to be very, very difficult. In fact, the number pi plus E might be algebraic and might be transcendental. We actually don't know over the rational numbers. And so proving that a number is transcendental turns out to be very difficult in practice. Despite that, from a measure theory perspective, almost all real numbers are transcendental. There's an argument in the notes where you can see that, but in particular, if F is any finite or countable field, and it has any extension, then there are at most countably many algebraic elements. In E over F. And the idea behind that is basically that there are only countably many polynomials of any given degree, and there are only countably many possible degrees, and so there are actually only countably many polynomials. So the set of polynomials with coefficients in f is countable, and we know from a previous theorem that any polynomial has a number of roots which is bounded by its degree. A degree n polynomial has at most n roots when working over a field, which we are. And so of all these countable polynomials, each of them only have finitely many possible roots. And so that means that there are only countably many roots of polynomials in f adjoin x. And these roots of polynomials are precisely the algebraic elements over f. And so what this means is that, for instance, again, considering the extension Q contained in R, since R is uncountable and Q is countable, this means that there are only countably many algebraic elements over Q in the real numbers, and so almost all real numbers are transcendental over Q. Now, our next goal is going to be to deal with the minimal polynomial of an algebraic element. It's going to turn out that knowing that this thing exists and being able to measure it are going to be very important to understanding the structure of algebraic extensions in general. So we move to Theorem 169. Let's let f contained in E be a field extension. A contained in E an algebraic element. Over f. There exists a unique minimal polynomial for A over f, and furthermore, if f is any polynomial over the field f such that f of a equals 0, that is, if f is where f is a root of a, or a is a root of f, sorry, I got that backwards, then the minimal polynomial, which I'll call p, divides. So there always exists a minimal polynomial. This minimal polynomial is unique, and so we'll from now on be talking about the minimal polynomial of an algebraic element. And if you have any polynomial who has a as a root, then that minimal polynomial will divide that polynomial f. So this minimal polynomial carries a huge amount of information about the element a. In fact, all the information that we could want about it from an algebraic point of view. So let's prove this. Now, what we're going to start off with is we're going to define an ideal of f adjoin x, and this ideal is going to be the set of polynomials in f adjoin x where f of a is equal to 0. We have that I is an ideal of f adjoin x, and this is an exercise, a fairly easy one. This construction where we look at all the polynomials that have a given number as a root, this is actually a special case of a much more general construction, which is sort of the basis of algebraic geometry. Algebraic geometry is the study of how the geometry of curves in space relate to algebra, especially of things like polynomials. And so in algebraic geometry, we will often look at the set of all polynomials that are zero when you plug in a given set of numbers, maybe just a single one or maybe a whole big collection of them. This is really a very baby example that we're using here, but it's got sort of the flavor of algebraic geometry here. So since this ideal I is an ideal of f adjoint x, we know that it's principal. Since f adjoint x is a PID, we have that I is generated by some single polynomial p for some p in f adjoint x. Now, since A is actually algebraic over f, it means that there is some non-zero polynomial that has A as a root, so I contains at least some non-zero element, which means that I is not equal to the ideal generated by just 0, and so in particular this means that the generator P of I is non-zero. In particular, this means that P has an associate which is monic. Basically, we can just multiply P by the inverse of its leading coefficient to get a monic polynomial. It will still be a generator of I. And so we may, without any loss of generality, just assume that P is monic to begin with, without changing any of the things that we've determined about P so far. So P is monic. Because P belongs to I, it is a polynomial that has A as a root. The only thing left to show that P is a minimal polynomial of A is to show that it's irreducible. So let's show that. Let's suppose that P is equal to G times H for some G and H belonging to the polynomial ring f adjoint X. Now, in E adjoint X, we have that X minus A is a factor of P, because A is a root of P that belongs to E, and so since E is a field and A is a root of P, that means X minus A is a factor of P. But X minus A is also irreducible, so that means that X minus A is a factor of either G or H. Without loss of generality, we may assume that X minus A is a factor of G, because there's nothing distinguishing G and H so far, so we'll assume that G minus A is a factor of G without loss of generality. So that means that G of A is equal to 0. So in particular, that means that G belongs to the ideal I. The ideal I, which is generated by P. So in particular, this means that the degree of G is at least as big as the degree of P, because P divides G. And so this means that we must have that the degree of G is equal to the degree of P, and the degree of H is equal to 0. So that means that H is a unit. And so what we did is we assumed that P is equal to a product of two things. We proved that one of those things had to be a unit. So hence, P is irreducible. So we've found a monic polynomial P, which has A as a root and is irreducible. Therefore, P is a minimal polynomial of A, and we have that P divides F for any F in I, because P is the generator of the ideal I. So we've proven almost everything that we need to in this theorem. The only thing that we have left is the uniqueness. We need to make sure that there isn't some other unique polynomial, that there isn't some other minimal polynomial for A. So now let's let K be any minimal polynomial of A. So that means that K belongs to the ideal I, and so K is equal to P times Q for some Q in the polynomial ring over F. Now, since K is irreducible, since K is irreducible and P is not a unit, we have that K is associate to P. So K is equal to some unit times P. But since both K and P are monic, they both have leading coefficients 1, which means that if K is equal to some unit times P, that unit must be 1. So that means that K and P actually have to be equal. So that finishes the proof that shows that there is in fact one and only one. There is exactly one minimal polynomial for any algebraic element over a field. This is a very strong existence and uniqueness condition, which is going to be absolutely essential to what we're going to do from now on when studying these algebraic extensions. Now, the next thing we want to look at is how algebraic and transcendental extensions work differently when we take the smallest extension field that contains each of them. Now, for the statement of the next theorem, recall that the notation f of x in parentheses is the field of fractions of the polynomial ring f adjoint x. That is to say that the field f of x is equal to f over g, where f and g are polynomials in f adjoint x, and g is not equal to 0, and where f over g is equal to h over k if fk is equal to gh. So this is just the standard definition of the field of fractions. We're looking specifically at the field of fractions of a polynomial ring, which is a domain, and therefore we can form its field of fractions. This f adjoint x is a field, and so we're going to show that when we work with transcendental elements, the field that we get is isomorphic to this one. So Theorem 170 says, let's let f contained in E be a field extension, and A any element of E. Now, if A is algebraic over F with minimal polynomial P, then the smallest field, containing F and A is isomorphic to F adjoin X mod the ideal generated by P as F extension fields, and if A is transcendental over F, then F adjoin A is isomorphic to the field f of x as F extension fields. All right, so before we get into the proof of this, I want to point out that the first part, where A is algebraic over F, this is something that we've already seen. We've actually already proven this because the minimal polynomial is irreducible. We've already shown that if A is the root of an irreducible polynomial P, then then the smallest field containing F and A is isomorphic to F adjoin X mod the ideal generated by P. We've actually already seen this. So the only new content to Theorem 170 is going to be the transcendental part here. And the thing that I want to point out about that is that this isomorphism here is true for any transcendental element over F. If you take different algebraic elements over F, they will have different minimal polynomials, say with different degrees. And therefore these fields, F of A, will look different. They'll have different dimensions as vector spaces and so forth and so on. However, if you take any transcendental element and look at the field containing the smallest field containing that transcendental element and F, they're all isomorphic to each other as F extension fields. The field F can't distinguish between two transcendental elements over F in any case. So again, this is sort of the motivation for the term transcendental. Transcendental element over the field F is an element that transcends anything that F understands. It transcends any polynomial equation in terms of F. And once things transcend what F can detect, they're all indistinguishable from each other. So as far as F is concerned, all transcendental elements over itself are the same. Because the smallest field containing it is always this isomorphic to just this F adjoin X. All right, so let's look at the proof of Theorem 170. If A is algebraic, this is simply Theorem 157. All right, so let's suppose A is transcendental over F. And we're going to show that these two F extension fields are isomorphic, and so we're going to build an isomorphism between them. So let's let phi from F of X to F of A be given by phi of F over G, and we'll have that be F of A times G of A inverse. So this is the most natural thing for us to do. Dividing by G, 1 over G is essentially G inverse. And so if we want to go from polynomials involving just X to something that is based on F, but also includes the element A, then we just basically take what we get if we replace all the X's by A's. So we've got this this function here going from F of X to F of A. And we're going to show that this function phi is an isomorphism of F extension fields. So we claim that phi is an isomorphism of F extension fields. Now, the first thing that we have to check is to make sure that phi is well defined. And the reason why we have to worry about that is because the elements of f of x are um, they have representatives. They're not uniquely described. F over g, rather, could equal h over k for totally different h and k. And so we need to make sure that if we're in that situation, that we get the same number, the same element of f of a out of it. Otherwise, this phi won't even be well defined. So we claim first that phi is well defined. So let's suppose that f over g equals h over k inside f of x. And so now we have that fk, the polynomial f times k, is equal to the polynomial g times h. So now we have that phi of f over g is equal to f of a times g of a inverse. Now this is equal to f of a times k of a. K of a is going to be something times k of a inverse times times g of a inverse. Now we might want to be careful here and say, okay, well, how do we know that k of a inverse actually exists? Frankly, we should have asked this back at the beginning when we, to show that phi is well defined, we need to show that g of a is non-zero. So since a is transcendental over f, it is not the root of any non-zero polynomial. So that means that g of a and k of a, in this case, are both not equal to 0. Because g and k are not allowed to be 0 inside the field of fractions f of x, and therefore, since they're not 0 polynomial, when you evaluate it at a transcendental element over the field f, you don't get 0. So that allows all of this to work. So continuing the equation, we have f times k. We know f times k is equal to gh. So f of a times k of a is g of a times h of a times k of a inverse times g of a inverse. And now we've got g of a and g of a, so we g of a inverse, so we get h of a times k of a inverse, which by definition is phi of h over k. So this shows that phi is well defined, both to make sure that the output that we get of it makes sense, because we're not trying to take the inverse of 0, and also that if we've got two different fractions in the field of fractions of f adjoint x, then they go to the same element inside f of a. We can use similar computations, actually even simpler ones, show that phi of f over g plus h over k equals phi of f over g plus phi of h over k for any f, g, h, and k, and phi of f over g times h over k equal phi of f over g times phi of h over k. In each case, you basically just evaluate both sides here by the definition and then observe that they happen to be the same, using associativity and distributivity and all of our standard ring theoretic stuff. So this means that phi is a ring homomorphism. Now, it still remains to show that phi is bijective and that it is a homomorphism of f extension fields. So now let's suppose that f over g belongs to the kernel of phi. This means that 0 is equal to phi of f over g, which equals f of a times g of a inverse. Now, g of a inverse is never equal to 0, so that means that f of a is equal to 0. Now, since a is transcendental over the field f, this means that it's not the root of any non-zero polynomial. And so if a is a root of the polynomial f, we must have that this polynomial f is equal to 0. So that means that f over g is equal to 0 over g, which is actually the same as 0 over 1, which is the 0 element inside the field of fractions of f adjoint x. Hence, the only element of the kernel is the 0 element, and so phi is injective. All right, so we've got that phi is an injective ring homomorphism. So we got phi from f of x to f of a is an injective ring homomorphism. In particular, we may note the following further. For any little x inside f, we have that phi of little x, which is the same as phi of little x over 1, is equal to just little x. Because this little x is not the capital X that we're using as our indeterminate. So in particular, this means that phi is a homomorphism of f extension fields. And in particular, this means that f is a subset of the image of phi. Also, we have that phi of capital X over 1 is equal to a, so a is also in the image of phi. Since phi is injective and f of x is a field, what all of this shows is that the image of phi is a field containing f and a. This means that f of a, which is by definition the smallest field containing the field f and the element a, is contained inside the image of phi, but by definition the image of phi is contained in f of a as well. So in particular, this means that the image of phi is equal to f of a, so phi is surjective. Hence, phi is an injective surjective homomorphism of f extension fields. And so in particular, this means that f of a is isomorphic to f of x as f extension fields. And that finishes the proof. So this means that we can find the smallest extension field containing an algebraic or a transcendental element and describe it in terms of the base field itself. So for example, the smallest field Q of pi containing both q and pi, which is transcendental over q, remember, is q of pi, and it's isomorphic to what we get when we take polynomials over polynomials. But this isomorphism is the one that just takes the variable to, or the indeterminate rather, to pi. And so it's of the form a0 plus a1 pi plus a2 pi squared plus etc. Plus am pi to the m all over b0 plus b1 pi plus b2 pi squared, etc., plus bn pi to the n, where the ai and the bj are elements of the rational numbers, and the bj are not all 0. So the smallest field containing both the rationals and pi consists of a bunch of numbers which look like this. And furthermore, you can tell when two of these elements are the same because they correspond to polynomials, fractions of polynomials that would be the same back in the original fraction field. Now, we could also look at Q of E, and it's going to look almost exactly the same. The only difference is that we got E's in here instead of pi's. And in fact, these two fields behave almost exactly the same because Q, the field Q, can't tell the difference between pi and E. They're both transcendental over Q, and so as far as Q is concerned, they behave exactly the same way when you include a field which has both Q and one of them in it.